then we're going to repeatedly find and remove the minimum priority vertex V in Q. So far this looks exactly like Dijkstra's algorithm, except that I said something different about how, somewhere up here about how these V's are computed, but so far there hasn't actually been anything different. For each edge, VW, if W is still in Q, and E of W is greater than the length of that edge, we set E of W to be equal to the length of that edge. And E of W equals B. So really the only difference here is in these two formulas, the comparison and the new value for these B values, I'm using just the length of the edge and not length plus the distance to V. Very small change, but this keeps these priorities equal to the best edge connecting each new vertex and adding them into the graph. And then when we're done, the minimum spanning tree is just the set of edges from every vertex V to its parent pointer. Except for S, who doesn't get a parent pointer. It always stays none. And that gives us n minus 1 edges, which form the tree. Yeah?
I'd say find and remove, what's that word? Minimum.
Find and remove the minimum priority, which I kind of abbreviated PRIO.
Okay.
The vertex whose D value is the smallest. And because it's essentially the same algorithm as Dijkstra's algorithm, tiny change to how we compute these priorities, the analysis is the same. So the time for this is the same as Dijkstra. And with a binary heap, it becomes O of m log n. The same time bound that I gave you for Dijkstra's algorithm short stack. But I wanted to tell you about another one, Kruskal's algorithm. One per vertex. And eventually this forest is going to be the minimum spanning tree, but right now it's just a forest. Move through the edges in that sorted order. And if you ever see an edge that connects two different trees, Now in this example, that doesn't actually give us a different edge ordering because we loop through the edges in sorted order. 3 connects these 2 vertices which are not yet part of the same tree, so we add it. 5 connects this vertex in this 2 vertex tree with 1 more vertex, so we add it. 6 connects 2 vertices that have already been connected, so we don't add it. 7 connects 2 trees that are different. We add that edge, etc., etc. So just loop through each edge, test whether that edge connects 2 different trees or 2 vertices in the same tree. Now that test, I mean, when you add an edge, you're always adding an edge that is the smallest across a cut between one of its trees and the rest of the graph. Because if there were a smaller edge, you would have already added it, and therefore this algorithm is correct by the cut principle. This test for whether they're in different trees. Can be done using a somewhat complicated but practical and efficient data structure called the union find data structure that I'm not going to describe. It takes a whole lecture by itself, maybe a lecture and a half. And it's really fast, so that the total time for the algorithm is O of however long it takes to sort those m items, n log n if you're using a comparison sorting algorithm, but maybe faster if these are small numbers and you're using graded sorting, plus m alpha of m. This is a non-constant, but a very slowly growing function. Much slower than log. Much slower than log, etc. You write down any number, fixed number of logs, log, and this is a slower function than that. But it is non-constant, so this is not really a linear time algorithm, even if you could sort it in linear time. In all practical applications of this, the sorting step is the slow step. This function is so slowly growing that for all conceivable inputs that you could write down using 1 bit per atom in the universe, it would be 4 or 5. So really slowly growing function, but non-constant. Yeah.
So what is this slowly growing function?
So it is, there's a quickly growing function called the Ackermann function, where Ackermann of x comma 1 is like x plus 1, Ackermann of x comma 2 is 2x, Ackermann of x3 is 2 to the x, Ackermann of x4 is 2 to the 2 to the 2 to the 2 to the x times. Each row, each successive row of this function is a 2-argument function. The second argument tells you apply the function in the previous row that many times. So, in the 4th row you get powers of powers of 2, and the 5th row you get something even more. How many times you repeat that power of powers of 2 operation, etc. alpha is a one parameter inverse of that function that says for what number x is the Ackermann function of x comma x greater than or equal to m. So you might imagine if already by the fourth row you're taking powers and powers of 2, it doesn't take many rows to get to an x for which the Ackermann function of x comma x is at least m. And that's what this alpha is. One more quick algorithm. Broca's algorithm. This algorithm requires all the edges to be different. The other two algorithms you can just use directly, even if there are ties. This one, we need everything to be different. So minor difficulty with using it, but in this case it works. Every tree T in the forest finds its smallest outgoing edge. And we simultaneously add them all. So this tree finds the edge labeled 3. This tree finds the edge labeled 3. This one has 5, 6, 10, and 12, so it chooses the one labeled 5. This one has 7, 10, and 11, so it chooses the edge labeled 7. This one has 9, 12, and 11, so it chooses the edge labeled 9. And in this case, actually, we get the whole tree all at once. So, but if we hadn't done that, if we still had multiple, you'll notice that the edge label 3 is found twice, by the way. That's okay. If we still had multiple trees left, we do the same thing again, but we ignore the edges that connect two vertices in the same tree and only add the edges connecting vertices in different trees. So the analysis is O of m per repetition and each repetition reduces the number of trees by at least a factor of 2. Because the worst case happens when, if you look at just these two trees, they're both connecting to each other, and so we get two trees that are paired up with each other. Every tree gets part of a larger conglomerate of trees, but the worst case is when all of those conglomerates are two trees pairing up with each other. And we get half as many trees as we did before. So every time we do one of these repetitions, we reduce the number of trees by at least a factor of 2. Here we reduced it by a factor of 5. Because we're reducing the number of trees by a factor of 2 in linear time, if you work through this carefully, you get O of m log n. So all three of these algorithms have the same running time. Because if you run the Grimm-Dijkstra-Yarnik algorithm with a binary heap as your priority queue, you get this. If you run Borovka's algorithm, you get this. If you run Driscoll's algorithm with a comparison sorting algorithm, you get this. But there are better algorithms known. We know how to find minimum spanning trees in order M randomized expected time. So like the linear time median finding, that sort of algorithm. It runs randomly. The randomness, the randomness is only random numbers that are chosen by the algorithm to try to make it faster. It's not in the input. We can solve it in this same nasty inverse Ackermann function. Barely superlinear without random numbers. Or there's also some algorithms that are order M, assuming that all the edge lengths are some kind of small integers and that you're doing integer arithmetic instead of comparison sorting. So it's still unknown and an open problem whether we can do order M time, non-random, in a comparison model. Because all of the algorithms that I showed you only need to look at the edge lengths by comparing them. And those algorithms have M log n time. You can do better in a comparison model, but we don't know whether we can actually get linear time. Okay, that's it for graphs. I will see you Monday for the midterm.